One of the major topics in this astronomy unit is the Hertzsprung-Russell diagram, or HR diagram for short. We talked a little bit about it, but I wanted to review a little bit for you. Just a reminder, it's a diagram developed to graphically classify stars by their temperature and their luminosity. Temperature is pretty self-explanatory. Their luminosity, however, is their brightness, how bright they are as they appear in the sky. Let's take a look at it. Here it is. You'll notice along the y-axis, here's luminosity, and it is increasing as we go upward. Luminosity is increasing as we go up, and temperature is on the x-axis. Let me get my pointer out here. Here we go. So we have luminosity increasing as we go up. Temperature is opposite, though. Temperature is increasing as you move toward the origin. Notice 40,000 Kelvin down here, 2,500 here. So the blue, the lavender stars are much, much hotter than the orange, yellow, red stars that we're talking about down at this realm. So let's take a look at these points. If you have a star and you're going to analyze the star, well, let's say it has a luminosity of 10 to the second and a temperature of 10,000 Kelvin. Well, that's going to be right about here. Okay, that's where we would plot our point. And it would fall within one of the many main sequence stars. 90% of the stars you see are main sequence stars. Now let's say it had a temperature of about 15 Kelvin and 10 to the negative 2 luminosity. It's going to fall down here, and it's not going to be classified as a main sequence star. It's going to be classified as a white dwarf. Okay, white dwarfs are down. They're a little bit more dim because they're farther down, but they are hotter. Okay, because 15,000 Kelvin, pretty hot. If we move up to this realm, okay, if we're looking at 2,500 Kelvin, we're cooler, but we're higher up on the graph, so we must be what? We must be brighter because we're up here. We're going to fall in the area of the giants, or if we're even brighter, we're going to be a supergiant. So let's look at what this tells us. If we find a star and we plot it here, what's its temperature? Well, it's going to be hot, right? We're talking about 30,000 Kelvin. What about its brightness? We're up here, 10 to the 6th luminosity. That's bright. So up in this quadrant, the stars are hot and bright. Let's move down. It's still hot down here, right? We're looking at 20 to 40,000 Kelvin. But what about their luminosity? Down here is not very bright. This is a dim star. Hot and dim for the white dwarfs. Over here, 2,500 Kelvin. Cool. And we're low on the luminosity scale. We're cool and dim. How about up here with the supergiants? Well, we're bright, but we're cool. Cool and bright. So, this is classifying these stars according to their luminosity and temperature. But can it tell us anything else? Well, let's think about it. If we are a star and we're way up here, look, we have supergiants way up high. We have dwarfs down low. We know, okay, kind of intuitively, that bigger stars are brighter stars. So if it's higher up on this HR diagram, it's going to be larger. So our larger stars are going to be up here across the top. And our smaller stars are going to be down here across the bottom. So it tells us luminosity. It tells us temperature. Now we know it tells us size. Okay. What else? What else might it tell us? Well, it tells us the age. It could tell us the age. All right. White dwarfs are going to be older stars than main sequence stars. All right. Main sequence are in their main adulthood. Giants going to be older. Supergiants older as well. So it tells us temperature. It tells us brightness. It tells us size, and it tells us age. There's a lot going on here, so hopefully we've got that.